Yeah, the board is visible, na?
Yes, sir.
Okay. So we were discussing carbonate, and in the last class we discussed the different controls on the carbonate generation, and we discussed that how the carbon dioxide pressure and it controls the carbonate generation. Now, even if that the carbon dioxide pressure is favorable, suppose the carbon dioxide pressure is favorable and the carbon dioxide pressure is not very high and it is conducible for the carbonate precipitation. Taking that, what are the other factors that basically control the carbonate precipitation? So it is not only carbon dioxide. Carbon dioxide actually put the first order control. What we should say, the first order control on the carbonate precipitation is the carbon dioxide pressure. That if you increase the carbon dioxide pressure in the water column, carbonate go into dissolution. If you decrease it, then the carbonate go into precipitation. Now, besides the carbon dioxide pressure, the other controls, what we control the carbonate precipitation, both in terms of depth-wise, the ocean depth-wise carbonate distribution, as well as the latitude-wise carbonate distribution in the. So, what two things? Number one is depth-wise, ocean depth-wise carbonate, and number two, the latitudinal carbonate distribution. One is with respect to depth, another with respect to space. So depth when we talk about the oceanic depth, and space when we talk about the latitudinal distribution. Okay. Now, what are the other factors that basically? So I first list out the factors, then we will discuss the factors. Number one measure is that when the carbonate will be maximum generated, at what place carbonate will be maximum generated? Where there is a maximum productivity. So if you have the primary productivity, then the food chain will start. Now in the food chain, the primary productivity, that is your phytoplankton. And that phytoplankton is being taken by the zooplankton. And from phytoplankton to zooplankton and the different invertebrate organisms. Suppose when we talk about bryozoa, we talk about chinoid, we talk about mollusk, we talk about foraminifera, we talk about any other organism. So they all come in the food chain at different stage. Okay. So the first thing what you require is the productivity, that is the phytoplankton generation. If phytoplankton generation do not have, then the food chain is not starting, and all other organisms that will be affected by that. So for that, what is important is number one is light. Light is very important because any photosynthesis, because phytoplankton, they basically work about the photosynthesis. So the light is very important. Number two is salinity of the water column. Number three, the oxygen availability. Number four, the nutrient availability. Number five, the water temperature. And number six is the sediment. This is what we are talking about, the clastic sediment concentration. So all these the different factors that also contribute in the carbonate generation. Fine. So this is what we call the typical concept of that how the carbonate that will be generated at a particular place. And these are the specific primary controls on the carbonate generation. First, we start with the light. Start with light. Now, as we discussed, for any photosynthesis and the primary production, the light is one of the most important control for the primary production or the photosynthesis or the primary the phytoplankton generation. So, if we see now see that depending, this is the depth. This is depth. This may be 1 kilometer, 2, 3, 4. Okay. So from on left side, you please draw it and then I am describing. Have you drawn it?
Yes, sir.
Okay. So what is being shown, if you go to the right side, that is the euphotic, oligophotic and apoptic. All these are based on the light penetration. The surface water of the ocean, where the maximum light penetration, that we call the euphotic zone. And then the light penetration that steadily decreases. And as it decreases, when you have the gradient of the light, that portion is called oligophotic. And where you really do not have any light that is penetrating, that is apoptic. Now you can see that the major carbonate production, that is basically coinciding with the euphotic or the early part of oligophotic zone. Now, what is euphotic zone? Maximum light penetration in the ocean water, the best that nearly 100% light penetration we get in the first 70 meter of the water column, and in cases it may go up to 100 meters. So first 100 meter of the ocean water column, that is basically considered the real high productive zone, which is called the euphotic zone. Okay. Now, this penetration of light, it will go up to what depth? It also depends upon that what is the siliciclastic supply in the coastline. If the siliciclastic supply in the coastline is very high, then the water becomes turbid, and in the turbid water, the light penetration decreases, and accordingly the productivity also decreases. So the siliciclastic supply it basically causes the carbonate productivity low. One of the major reason is that the sericiclastic supply, it cuts down the first cycle of the food chain, that is the phytoplankton generation, because any sericiclastic supply make the water column turbid, and thereby the light penetration in the water column decreases. Okay, is it clear?
Yes, sir.
Okay, now we come on to the other factors. Can you see all the diagrams? Right
Yes,
one.
sir, the third one.
Hello? Third one is not visible.
Yes, sir.
I will show you. Rest two you have already did it. Can you see the right one? 0, 1.025, 1.026, 1.027, 1.028. Is it done?
Yes, sir.
Okay. So by these three diagrams side by side, what I tried to show you is the physical condition of the ocean water column. Physical condition. This first diagram, that is the thermocline, is well known to you, that the temperature in the first 1 kilometer depth, the temperature drastically decreases and it goes below 5 degrees centigrade. Then you get the salinity. Salinity, it is maximum in the top about and then salinity decreases as you go, because salinity increases at the top because of the evaporation, because it's contact with the air and the continuous evaporation that causes the salinity to increase, and as you go down that the salinity decreases. Okay, and the density also, the density that is changing, that is what we call the pycnocline. So you have the three different boundaries that form. One is the thermocline, another is a halocline, and then the pycnocline. These three basically control the distribution within the seawater. Right? Now, the other controls which I have already discussed, these controls are basically the oxygen saturation and the nutrient supply. Now, question is that if this is the condition of the seawater, then how will be the distribution of the productivity in the seawater? That is the primary question. And so, what will be the general tendency of the deposition in the shallow water and the deeper water? So the general tendency, what we will be expecting in the shallow water, the more of aragonite and high Mg calcite, that kind of mineralogy, whether it is the organic paste or the cement, the aragonite or high Mg calcite, that will be more stable in the top part, because this is the most favorable part. When you have the high temperature, the lesser carbon dioxide pressure, the density of the water column is low, and then this is the best, the top portion, and there where you have the maximum, the eutrophic zone, the light availability, that is the best possible zone where you get the most favorable and maximum saturation of the carbonate mineral. As you go down, as the temperature goes down, your salinity goes down and your density goes high. So what you basically have, your pressure goes high, your light goes down. So all these, they are the counterproductive for the carbonate, and the carbonate will not be stable if we go more and more deeper in the ocean. This is the basic message. Am I clear?
Yes, yes.
Okay. Now, coming on to the other factor, that is that is a very important factor, in fact, for the carbonate precipitation. That is the question of the nutrient supply. So nutrient supply, that how we basically consider the nutrient supply. When we talk about nutrient and the productivity, then basically we talk about the four different elements, that is the nitrogen, phosphorus, and in some cases iron and silica. These are the four elements which are absolutely necessary, because without nitrogen and phosphorus, You know, even in our bones, the main constituent of our bone is phosphorus. And without nitrogen, the hormone system does not act. So, for any kind of the organism, the nitrogen, phosphorus, iron, silica, these are absolutely necessary. Now, in art, in world, what really happens? How these nutrients get supplied so that the productivity happens? For this, this is basically guided by two factors. Number one, the Coriolis force, and number two, the wind shear on sea surface. These are the two factors that basically is responsible, and how that we will be now telling. How they are basically controlling the nutrient supply. Yes, nutrient supply will be basically from the continent, because all these elements, they are basically being brought out. Ocean cannot generate this. All this has to be brought from the continent. But even then, their supply, their concentration, their oversaturation in the water column, where the productivity, how that happens, how that. For this, the Coriolis force, as you know, this is the first factor. That anything on the surface, I repeat, anything on the surface of the earth at the equator, which is on the surface of the earth, that is moving at a rate of 1500 kilometers per hour, because the earth is rotating. And anything which is in the mid latitude, 45-degree latitude, that is moving at a rate of 760 kilometers per hour. Am I clear what I am saying? Is it getting clear to you? I am describing Coriolis force. What actually is Coriolis force? Anything which is in the equator that is moving at a velocity at a rate of 1500 kilometers per hour, because earth is moving and we all are moving, and we are, because of the gravity, we are not feeling it. We are not feeling it. And in the mid latitude, because the rotation of the earth, the velocity is not same in all the latitudes. In the equator, the radius is maximum and the rotational speed is maximum. As you go away from it, that the rotational velocity that gets decreased. So in the mid latitude, it is this difference in the velocity. This difference in the velocity that is responsible for the formation of the Coriolis force. How? That if any object which is free from the earth, suppose air, water, that is free from the earth. Free from the earth means that it is chipke hue nahi hai, it is not attached with the earth. That free flowing object, air or water, if they are in the northern hemisphere, if they move northward, if it tries to move northward, it will be veered towards right. It will be veered towards right. Okay? And in the southern hemisphere, it will be veered towards left. Am I clear? Am I clear?
Yes.
Yes, sir.
So in the northern hemisphere, it will be veered towards right, and in the southern hemisphere, veered towards left. So what will happen? That there will be, I will be experiencing the westerlies in the mid latitude. Westerlies in the air flow from the west, because it is veered towards east, right, and so from the air will pass from the west to east, and in the equator the air will move from east to west. So from in the mid latitude, the air will pass from west to east, and in the equator, because of this, the air will pass from east to west. Okay, and this, the movement in the mid latitude from west to east and the equator in the east to west, this will form the large scale oceanic gyres. Oceanic gyres. Large scale oceanic gyres. Okay. What will happen that these oceanic gyres, they in the mid latitude, they will form the mid latitude currents. The mid latitude currents. Okay. And if in the continent in the northern hemisphere, along their western margin, these mid latitude currents, they will be basically taking the water towards the pole. In the, am I clear what I am saying? Is there any problem? Please stop. If there is a continent in the northern hemisphere, in their western margin, these mid latitude currents that will take the surface water towards the pole, and from the cold water through eastern boundary of the continent, they will come towards the equator, to the eastern coast. So from to the western coast, that the movement of water is towards the pole, and the eastern coast, that they will be coming to the equator. So this circle, I think this has already been discussed with you in other courses as well, isn't it?
Yes, sir.
Yeah. So you are more knowledgeable than me. So let me ask you that what is Ekman bearing? Hello. Hello.
Yes, sir.
What is Ekman bearing?
So due to Coriolis force, the ocean waves get deflected towards 45 degree towards the right from top to bottom.
नहीं वो तो मैंने अभी बताया, तो अभी भी मैं भी तो बताया। एकमैन बियरिंग क्या है? हेलो, can you listen to me?
Yes, sir.
Okay. Ekman bearing, yes, you can see, but I exactly want to know what is Ekman bearing.
So from top to bottom, they get deflected towards 45 degree, 45 degree. Then the resultant is almost 90 degree in the northern hemisphere.
Exactly. So exactly what she has said, she is right, that the Ekman bearing is that the wind, and with respect to depth, the vectors, the length of the vector, actually this length will be further less. This will be further less. So actually what happens that when wind, as you go depth, that the length of the vector will reduce. Length of the vector is reduced, and it will assume more angle than the wind direction. So as it assume a more angle with the wind direction, then you get the total bearing of the oceanic current. Now, as you are aware of this thing, that what is my intention, why I am connecting it with the nutrient supply. This, exactly this, what will happen, that this will cause the upwelling, because that when you have a low pressure zone that will be developed in the western margin of the continents, western margin, because you are in the western margin, you are taking away the water from towards offshore. You are taking away the water in the offshore, in the that we have already discussed. So when you are taking away the water in the offshore, there will be a low pressure near to the coastline, and then the deep water, the nutrient rich deep water which is coming from the polar region, they will be upward. They will be upward. Am I clear what I am saying?
Yes, sir.
Yes, sir.
And that upwelling will bring all the nitrogen, phosphorus, and all this material onto the coastline, which will cause the more productivity of the garden. Okay. Okay. So I think you people could. In case of equator, because the entire flow is from the east, whether it is northern hemisphere or in the southern hemisphere, so always in the equator there will be upwelling, because it is the flow from the east and in the north and south, so there will be the upwelling in the equator, so there will be always a better productivity near to the equator. But if you go away from the equator in the mid latitude, the upwelling you can only expect in the western coast of the country. Okay, now once we have discussed all these things, then we come on to the composition of carbon. Composition of carbon. Any carbonate, it is made up of two components. One is called allochemical component, another is orthochemical. This allochemical component, they can be of four types. One, bioclast, void, pellet, intraclast. In orthochemical component, there are two components. One is micrite, is pyrite. Now, if I draw So this is a representation of a carbonate under microscope. What you can see, there are bioclast, there are void, there are pellet, there are intraclast, and they are bound by two kinds of material, micrite and sparite. So what in the siliciclastic we get as a framework, matrix and cement. In case of carbonate, it is allochemical constituent and orthochemical constituent. Allochemical constituents is just like the framework of siliciclastic. Here we call it a allochemical, and they are, instead of quartz, feldspar and all this stuff, here we get the bioclast, void, pellet, interclast. And they are bound by either Mott size particle. If it is a Mott size particle, Mott size, then you call it a micrite. If it is a sand size, then you call it a sparite. Sand size, then you call it a sparite. Okay. Now we'll discuss this different allochemical constituent. First, start with the bioclast. Then, what is a bioclast? Bioclast is any organism. Suppose I have a mollusk, I have a crinoid, I have a bryozoa, I have a gastropod, a polycipod, a foraminifera. They are tastes. That is a bioclast. Now, what will be the composition of this taste? It all depends upon two factors. That at what depth of the ocean that organism is most favorable to grow, and what is its vital factor. So that basically controls that with what kind of minerals it will make its taste. Many of the organisms, they form taste by means of aragonite and high Mg calcium. A few also form their taste by means of the low Mg calcium. So what will be the preference of a particular organism to make their taste? It fully depends upon the depth, the relative saturation of carbonate in the water column at that depth, and its vital factor based on that. But one thing is clear, that after the death, the soft part of the organism get decayed, and the hard part made up of carbonate minerals, they get settled. Then by bacterial degradation, by microbial activity, or by means of any high energy, suppose high tidal current, storm, they get broken into fragments. This taste. And this taste, what will be the composition of this taste, that will be fully dependent upon that how these tastes are made by the organism during their living position. So the bioclast can have any mineral. It can have a totally aragonite, it can have a mixture of aragonite and Mg calcite, it can be Mg calcite, it can be low Mg calcite, mixture of aragonite and low Mg calcite. So I can have all the variations of the composition of the bioclast. But one thing is clear, that what kind of bioclast I expect when I talk about the distribution of carbonate. Distribution of carbonate in the latitude wise, then I will discuss that. That I will discuss afterwards, after I discuss all this. So this is bio. Now coming on to void. Void is also referred to as a coated grain. Coated. Now what is void? Void will have a nucleus. This nucleus can be anything. It can be a sand grain, it can be a fish teeth, it can be a wood fragment, anything. And then around that, the carbonates start growing in the form of concentric layers. Concentric layers. Now, you see, if the grain is a settled grain, if this initial nucleus is a settled grain, and it is not moving, then you can only develop the carbonate as a half circle. You cannot develop carbonate in lower. To make it a full circle carbonate coating, you have to continuously energize the grain. grain has to be in motion always. And then only you can have the full circle of the carbonate growth around. Is it clear? And that means that any void growth that will be always favored in a high energy condition, and we get the void shoals in the high energy condition. Is it clear that why void always indicates a high energy condition? Okay. Now, voids present day, the voids what we are getting, those voids are mostly the high Mg and aragonite minerals. Present day, whatever voids, the present day modern ocean voids are forming, they are aragonite. But many of the ancient voids that we get in the rock record, they have a calcitic mineral. They have a calcitic mineral. So what I am saying, modern voids, they have aragonitic mineral. Whereas in the rock record, the ancient voids, they show calcitic mineral. So then it became a question among the workers that why modern voids are all aragonitic and the ancient voids are all calcitic. Why it is happening? That why ancient voids are all calcitic? Then when the ancient voids, they were seen under microscope, they found that there are two kinds of texture that was observed in the voids. In one kind of texture, the voids, we get a radial texture. And in another kind of voids, they show concentric texture. This is a radial, this is concentric. What I am saying, modern voids are aragonitic. But when we see the voids in the ancient, suppose Paleozoic carbonate platform, and there you get the voids, you see that they are mineralogically calcic. When those calcitic voids, they were seen under microscope, that you are basically, you get the voids showing two kinds of texture, internal. We'll show this. ऐसे तो in the carbonate practical I used to show all these things, but I do not know this year how I will be showing those things. They show radial and concentric. Now from this radial and concentric, then the people came to the view that those which are radial, they are actually the aragonitic void diagenetically transformed into calcite, because aragonite by means of needles, they grow radially. So the radial voids, they are basically originally aragonitic, then now diagenetically changed into calcitic. Whereas the concentric voids, they were originally calcitic. They were not changed because they were originally calcitic, so there was no necessity of their further change, because that is the stable mineralogy. Because aragonitic, because of unstable, they got changed into calcite, but preserved its radial geometry. Now, when in the geological rock record, through the different geological time, suppose Paleozoic, Mesozoic, Cenozoic, the different time, the voids that were studied, and it was found that in some time the voids are of aragonitic mineralogy, and in some time they were originally calcitic mineralogy. So people see then why sometimes there is a bias in the void, they become aragonitic mineralogy, and why sometimes there is a bias that there is a calcitic mineralogy. Then finally it came to the view that this mineralogy, original mineralogy of the void, it is a function of the carbon dioxide pressure in the atmosphere and the relative stand of the sea level. Relative stand of the sea level. Okay? What they found, that when the carbon dioxide pressure is low, that means the sea level stand is low because carbon dioxide pressure is low. That means that there is the lesser carbon dioxide pressure is low. That means there is the better uh, more saturation of the carbonate that is available. The carbonate saturation is better, and carbonate saturation is better, and the carbon dioxide, because carbon dioxide pressure is low, there is more favorable for the glaciation period, and the sea level stand is low. In that case, because of the favorable condition, the unstable mineral like aragonite that was formed. But when the carbon dioxide pressure was high, means when the sea level is high, there were more deglaciation. Then there are more unfavorable condition. So the voids become the more calcitic. So the ancient voids with their original aragonitic and calcitic mineralogy that were used to reconstruct the ancient sea level stand. The ancient sea level, the high and low, that was basically established. So you can see the ancient. So So based on the original mineralogy of the void, the whether it is calcitic or it is aragonitic, a first order paleo sea level curve that would have been drawn because of the times of high sea level and the low sea level, and that so it is a sea level high, so it means CO2 pressure high, low CO2. So this is what we call the greenhouse globe, and this is what we call the ice house. So a greenhouse ice house concept, was drawn by the void. Is it clear?
Yes.
Okay. Now we come on to pellet. Now pellet is a microcrystalline carbon, micritic carbon. Pellet is micritic. Pellet is micritic carbon. And it can be, because by the term pellet, it doesn't mean any biogenic or abiogenic origin. If this is abiotic origin, then it call it pelloid. If it is biotic origin, then it will call it fecal pellet. When we talk about the pellet, we only talk about that it is a microcrystalline carbonate grain. So any grain which is microcrystalline. Now it may happen that somewhere there is a micritic limestone. There is a micritic limestone, and from there a fragment that is broken and came here as a micritic fragment. In that case, it is totally abiotic. It is formed from a micritic limestone, and by the erosion from a micritic limestone, we call it the paloid. It can also be formed, the similar grain can also be formed as a fecal pellet. That means the organisms, they basically consume mud and by their excreta. That is, fecal pellet is the excreta of the organisms, which is actually the carbonate mud. Now these fecal pellets, then how we distinguish between a abiotic pellet and the fecal pellet? There will be high organic matter within the fecal pellet. They normally are brownish in color, and normally what we see, the fecal pellets will be very well, size-wise very well sorted, because the same population of organisms of same age, they will have the same fecal pellet size, whereas the paloids can be of any size, so they are likely to be of ill sort. Now, if the size is more than 2 mm, the pellet, the size is more than 2 mm, then we call it aggregate. What is the aggregate? Aggregate is pellet, wood together bound by cement, carbonate cement. So 2-3 grain, when they are bound by carbonate cement and form a grain more than 2 mm in size, then you call it aggregate. Okay. Now coming on to intraclast. Intraclast. It is a rock fragment, carbonate rock fragment. Carbonate rock. Okay. I just want to ask you one question. Can I have cross stratification in a carbonate rock? Hello? Can I have cross stratification in a carbonate rock? Anyone?
Yes, sir.
When?
So when the if the grains are more in the sand size and with the high energy, it can create the cross certification.
तो क्या कौन बोल रहा है? तुम?
Yes.
No, I am asking the students. Students, can we have cross stratification in carbonate? चुप क्यों हो? कुछ तो बताओ यार. तब चुप हो. Yes, we can have cross stratification in carbonate. When a carbonate rock acts as a source of sediment. Suppose a carbonate rock, because there is an original carbonate. Now this carbonate rock is supplying the sediment because it is acted upon by high tidal current, storm current, or any oceanic current, or it may be suffered a kind of the basinal jerk by earthquake, or the waves are pounding on it and breaking it. So if the carbonate rock, it becomes a source and it is supplying the carbonate particle, then the carbonate particle will behave like a detrital particle. And if the carbonate particle behave like a detrital particle, then any kind of structure that can form in a clastic rock, that can also form in the carbonate rock. Students, is it clear or not? Please respond. Make a sound.
Sir, please repeat once again.
Yeah. What I am saying that when we talk about that carbonates are chemical precipitation, carbonates precipitate from the water column. So if till now I am only discussing this, and this will not support that any carbonate rock will have the same structures what we get in the siliciclastic rock, such as a cross stratification, Hamocky cross stratification, everything that it doesn't support. But it is true that all these structures can also form in the carbon. When the carbonate is supplied from a carbonate source rock. Suppose there is an original carbonate rock in the Bering Basin, carbonate already deposited. Now that carbonate rock is coming under the action of high tidal current, storm, or there is the wave pounding, or there is an earthquake and jerking, by which the carbonate rock that is getting fragmented and breaking, and that is supplying clast. Now that clast, when it is supplied from a carbonate, original carbonate source rock, that clast then that clast will be acting with because of any flow, just like the same way as a siliciclastic grain that is transported, because carbonate is transported as a fragment. So it is a fragment of a rock now, and a fragmentary texture. So that will create all the structures that is commonly formed in case of siliciclastic. So yes, carbonates can also give me all the structure, provided that the carbonates in that is supplied as a clastic grain from a carbonate source. Am I clear?
Yes, sir.
Now, again I come back to the concept of intraclast. What is intraclast? Intraclast is that any lithic rock clast which is formed within the basin. Within a basin, the clast is formed within a basin. Now, within a basin, if a original carbonate platform that is supplying the sediment, that we call the intraclast. So, how I identify the intraclast? Intraclast is something like this. Suppose this is the intraclast. What I will get, that there will be lyoclast in it, there can be void, there can be keloid, and then it is bounded by spherite. There can be micrite as well. And the whole thing is in form of a clast. That means the original rock fragment, it is now broken and it has now become a clast. This is called intraclast. Okay, and suppose if it is within a basin, if the same intraclast that is come from outside the basin, then I call it a extraclast. And in a extraclast, I already showed you in the practical class, you will always have a oxidation ring. Iron oxide ring. Do you remember that day we were showing you?
Yes, sir. Yes, sir.
So that oxide rim will show that it had a subaerial transport. If that rim is not present, that means it was always underwater and there was no chance of the iron to get oxidized into iron oxide. So this is intraclast. Now, depending on, and I have already discussed the orthochemical constituent. Now, depending on the relative percentage of these allochemical and orthochemical constituent, the carbonates are classified. There are two different schemes of classification. One is Dunham classification another is Hope classification. In the Dunham classification, how is the Dunham classification? Let me tell you. This is Dunham classification. What is Dunham classification? That matrix supported, that means, what is matrix supported here? The entire carbonate is of orthochemical constituent. The allochemical constituent is less than 10%. If the allochemical constituent is less than 10%, then you call it a mudstone. It is also called calcistone. Calcistone. Okay. Then if you have more than 10% grain, again I am telling you what is the grain here. Grain here, bioclast, void, peloid, interclast. These are the grains. Then you call it rockstone. Then if the matrix content, they become grain supported. Then there can be some matrix, then you call it a packstone. There is no matrix, you call it a grain stone. And bound stone is that where there is a carbonate structure. Suppose a coral reef, that is a bound stone. A coral reef is a bound stone. That means the entire structure made up of limestone. Now how is this classification? This classification is basically based on the visual estimation. That when you see a carbonate rock, in the you identify how much will be the percentage of allochemical constitution. Oh, it is less than 10%. So you then name it a mudstone or calcistone. It is a visual estimation, and you need not have to see under microscope. You need not have to see under microscope. So it is a gross estimation of allochemical and orthochemical constituent. This is Dunham classification. So some people started criticizing it, and then the Fock classification. Now in the Fock classification is entirely the microscopic observation. Entirely the microscopic observation. So in the microscope you are identifying whether your allochem is a bioclast, a void, peloid, or interclast. And your orthochemical is a micrite or sperite. That and that. And accordingly, depending on the dominance of the bioclast and depending on the dominance, you name it biomicrite or biosperite, like that, oosperite or oomicrite. Or if you have two, three all together, you have bioclast, void, and peloid, and the ground mass is mostly speritic. And within bioclast, void, and peloid, the maximum percentage is of bioclast, then the void, and the least is the peloid. Then we call it pale biosperite. So the least abundance first, then the next, and the highest abundance last, and then the sperite. This is how it is made. But you see, here you are characterizing the allochemical constituent, characterizing the orthochemical constituent, and naming the rock by particularly identifying the allochemical and the orthochemical constituent. So this is microscope. Now, both these classifications are operational side by side. Whereas the Dunham classification, that is basically geologists, they follow when they are in the well site. Continuously the cores are coming and you have to do the logging in the well site. There is no scope of seeing, making a thin section and seeing under microscope. But you have to write a description of the rock, what is coming from the surface, subsurface to the surface. So there, the only thing is your visual estimation, and you have to follow the Dunham classification and write the description. But if you do a high-end one, you have the time to make a thin section and see it under microscope. Then in the laboratory, the Polk classification, that is more. So the both Dunham and the Polk classification are operational, whereas Dunham classification is an on-site practice work. The Polk classification is a laboratory based. Am I clear?
Yes, sir.
And that is the need of the both the type of classification. Okay. Now, if you see the distribution of carbonate, we have discussed that the distribution of the carbonate, that the tropical area, they are the best in the carbonate distribution. So the tropical area and as you go more towards the temperate and the polar region, then the carbonates, they will be lesser and lesser because they are not the favorable condition. What people have observed, that the distribution of the carbonate, depending on the it is favorable and the not favorable, that also varies from the equatorial to the pole. The assemblage of carbonate, what you will find in the equatorial region, that assemblage we refer to as the chlorozoan assemblage. Chlorozoan assemblage. And the assemblage what we get in the cool temperate and polar region, that we refer to as the Boramol assemblage. What are those? What is chlorozoan and what is? In chlorozoan assemblage, we get coral. Okay, and green algae, and all non-skeletal component, skeletal component. What are non-skeletal components? Void, paloid. These are all non-skeletal. Bioclast is a skeletal component. Bioclast is a skeletal and non-skeletal component. Because why? Because any non-skeletal component, that is basically is formed by the saturation and oversaturation of the water column. Suppose in a void, how you generate the coatings in the void? By means of precipitation of carbon dioxide from the water column. There is no biological or vital activity to scratch the carbonate from the water column, as the bioclasts are doing. By their vital activity, they are scraping the carbonate from the water column. Void is not that. Void is that there is saturation and oversaturation in the water column, so they are precipitating, and it is a high energy condition, so the continuous rolling of the nucleus allowing the circular growth of the carbonate lamina. So they are non-skeletal component. Whereas in a Boramol, what you get? to get bryozoa, okay, the mollusk, echinoid, and skeletal component. No non-skeletal, no non-skeletal. No non-skeletal. Okay. Is it clear? You also get here the radial. Radial. This is a first order differentiation. This is a first order differentiation that you may get that is chlorozoan assemblage and phoramole assemblage, and you will get a first order differentiation between the two, that how they are distributed in from the equator Is it clear? Hello?
Yes, sir.
Okay. Can you see the diagram?
Yes, sir.
So this is latitude, and this side we are showing the percentage of chlorophyll percentage. Chlorophyll, as you know, the chlorophyll is that material that is the responsible for the photosynthesis, isn't it? And accordingly, you have the eutrophic, mesotropic, and oligotropic. And you have phytozoans, the phytozoan, heterozoan, and the heterozoans. So what you get, in case of the subtropical, you are basically getting a oligotropic, and they are more phytozoans. Phytozoans means that phyto, what does it mean? That it has the more the botanical constituent, plant constituent. And as you go towards the more of the polar region, that they are changing to the heterozoa. And this I have already described to you, that the poramole and the chlorozoan association. So subtropical, the protozoans, they basically belong to the chlorozoan association, and the polar region, the heterozoans, they belong to the poramole association. And in the warm tropical, you have the transition between the two, which is a mixture of the phytozoan and the heterozoan transition. Is there any question? If there is no question, we'll end the class now. Okay? Because the next, my major discussion, that is the carbonate diagenesis. Because we have now discussed that what is the distribution of carbonate, what are the controls of carbonate, what is the mineralogy of carbonate, composition of the carbonate, all these things that we have discussed. Now after this, we will be landing into the carbonate diagenesis, which is a major part of carbonate discussion, carbonate diagenesis. And I don't want to start the carbonate diagenesis today. So tomorrow we'll start carbonate diagenesis. Till now, if you have no question, I will end my class now. Okay, and then at 2:30 we have a practical class.
Okay, sir.
Okay.
Thank you, sir.
Thank you, sir.